Good evening, everyone. Shall we start the session now? Okay, so let's start the session now. We will be doing week 7 today. We have already completed week 6. Yes, Abhishek, you were saying something?
No, sir.
Okay, I hope my screen is visible. So we have already completed week 6. And now we'll be starting with week 7. So in week 7, we have covered two concepts as of now. The first was equivalence and the second was similarity. So let's solve some questions on them. Okay. Before we move ahead, there is one more thing that I guess we can do before starting with equivalence and the similarity of the matrices, and that thing is called change of basis. So, what change of basis is? Okay, so I'll just give some of the hints. So, we let's consider we are given two bases. The very first basis is this. Let me call it B1, and it is my 1 comma 0 and 0 comma 1. Similarly, I have my second basis as well, and I'm calling it my beta 2, and that is, let's say, 1 comma 1 and 1 comma minus 1. See, when we talked about bases, we saw one thing, that bases are not unique, they are different, right? And here we can see both B1 and B2 are bases of your R2, right? Both are bases of your R, correct? So now in the week 6, we saw that we have coordinate vectors, and coordinate vectors are defined on some basis. So let's say we have a given coordinate vector v, okay, and that v was defined on the basis b1. Okay, that basis was defined on v1, and that coordinate vector is, mm, let's take it as 2 and 3. This is my coordinate vector. So a coordinate vector defined on basis b1 is 2 comma 3. What is b1? b1 is my this basis. Now, how can I find a coordinate vector defined on the basis not b1 but b2? Same coordinate vector. Okay, how to find this thing? Any idea? Any idea how we can do that? Anyone? How we can use the concepts of transformations to do that?
So, like first we can find the transformation for this these two bases, b1, beta 1, and beta 2,
Okay,
and after that, what we can do, we can multiply this um,
this coordinate vector with
transformation,
that.
yeah, vector with that, and I think we can get the
Okay,
beta.
so
Yeah.
let's continue with the same idea. So here we are going to use one thing that is called identity transformation. So what identity transformation is, it's defined as whenever you define a transformation. Okay, so I'm writing it as I because we are talking about R2. So let's stick to R2 only. So it's from your R2 to again R2. So I have this identity transformation defined from R2 to R2 and how we define that. So it's interesting. It's like from XY equal to XY again. Means whatever your input would be, you would get the same output. So this is what we call identity transformation. But we saw that whenever we want to get a new transformation matrix, whenever we want to get a transformation matrix, that depends on three things. What are those three things? The first thing is the definition of your transformation. Second thing is the basis of your domain. And the third thing is the basis of your codomain. Okay. So what I am doing here is I am taking, um, let's say, this B1 as the basis of my domain. So let beta 1 be the uh, basis of domain and beta 2 be the basis of the codomain. Okay, so if I have beta 1 as the basis of domain and beta 2 as the basis of codomain, how my identity transformation would look like? It would look like this. Then the matrix associated with the transformation would be represented as, I guess, this. Here I have my beta 2. Sorry. Okay, just give me a second. Here I have my beta 2 and here I have my beta 1. It would be represented it's something like this. So now just tell me what would be how to find this I of beta 2 beta 1. How can I find this matrix? Now this is what we used to do in week 6. Any idea?
So like here you have defined the identity transformation as like I of x comma y is equal to x comma y. Like it is the definition or something. Um, you are giving
Yeah, the
expression only.
identity
Like
transformation is defined as this only. That whatever your output is, whatever your input is, your output is same. So there is no difference in your input and output. So if you have a transformation like this, so then you call it an identity transformation.
so, sir, here we can directly like use this beta one and beta two. Like we put the vectors of beta one for the transformation, and we can find the coefficients. Uh, since here we are going to get the same thing because beta 2 is
Okay.
another
So,
vector,
oh,
and we can get the coefficients and put it as a column as to find the matrix.
okay. So how we usually find a transformation matrix? What we do, we try to find the we try to express the vectors of our codomain as the linear combinations, right? So let's represent the vectors of codomain as linear transformation. So it's going to be 1 comma 1 plus x plus y times 1 comma minus 1, correct? Now, uh, I must equate it with what? I of, let's take 1 comma 0 first, correct? And what is, it's going to give me 1 comma 0 only because I of x comma y is equal to x comma y only. So what would be the value of x and y in this case? X would be what? 1 comma 2, correct? And y would be 1 comma 2 as well. Okay, so maybe I should write it as x equal to y equal to 1 comma 2. So here I got my first basis vector, right? A first vector of this identity matrix. Now similarly I have done for 1 comma 0, I'll do for 0 comma 1 as well. So what I would do in that case, I'll just do x times 1 comma 1 plus y times 1 comma minus 1 is equal to I times of 0 comma 1, and that is going to give me 0 comma 1 again. So from here the value of x would be 1 comma 2, I guess. Again, oh sorry, my bad. The value of x would be 1 comma 2, and the value of y, is going to be minus 1 comma 2. Is it fine? So what would be my matrix? My matrix would be uh, this. Here I have 1 comma 2. Uh, okay, copy that. 1 comma 2 and 1 comma 2. We write it as column vectors, right? And here also I have 1 comma 2 and minus 1 comma 2 this time. So this is my transformation identity transformation matrix, or you can say the basis transformation matrix. Okay, so any coordinate vector that is defined on the basis B1, if I pre-multiply that coordinate vector with this matrix, so that would give me the corresponding coordinate vector defined on the basis beta 2. What does that mean? That means if I want of not beta 1 but beta 2 instead of 1, if I want beta 2 over here, so what I can do is I just need to pre-multiply this matrix with anything like this. Okay, so what would be the case here? Here I am just pre-multiplying this thing with 2, 3, which was given to me. Okay, and that gave me what? I guess it should be mm, 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 mm. It was going to be 5 by 2, and this thing is going to be minus 1 by. Okay, so is this thing fine? Change of basis. How you can change a basis? This is the method that you follow. If you are given a coordinate vector in B1, if you are given a coordinate vector with respect to the basis B1, and it is asked that what would be the coordinate vector with respect to the basis B2, then first you find the identity transformation, and then you use this. At whenever you want to change the basis, just pre-multiply it with this identity matrix, and your basis would be changed. Okay, any doubts in this one?
No, sir.
Okay. Then we had this thing called equivalent matrices. So what are equivalent matrices? Two matrices of order m cross n are said to be equivalent if you can find two invertible matrices. See, it's very important for the matrices to be invertible. So if they are invertible, this automatically suggests that their determinant is non-zero and they are square matrices. So P and Q both are square matrices with non-zero determinant. Okay, so if it's a m cross n matrix, so the order of P must be m cross m and the order of Q must be n cross n. One more thing you will notice, for two matrices to be equivalent, A and B to be equivalent, they must be of same order. So let's say you are given a set of matrices, a pair of matrices, and you are asked whether the matrices are equivalent or not. And you see the order of both the matrices are different. One matrix is of order 3 cross 4 and the another matrix is of order 2 cross 5. So you can directly say that the orders are not equal, hence the matrices are not equivalent to each other, right? So this was one of the things. So this equivalent matrices, the entire idea stands on this idea of change of basis, right? You had something defined on a particular basis beta 1 and gamma 1, and then you are saying that the same thing, if is defined with respect to another basis beta 2 and gamma 2, what it would look like, right? So if you have a transformation matrix which is defined on the basis of vectors beta 1 and gamma 1, and you are defining the same transformation matrix, but this time with respect to beta 2 and gamma 2, then both the matrices would be considered equivalent to each other. That that is what the idea of equivalent matrices is, the understanding of equivalent matrices. So any doubts till this point?
So can you explain the second point again?
Okay, the second point is, see what equivalent matrices are. If I give you any transformation, if I give you any function, okay, transformation is nothing, just a mapping, right? So in the week 6, we saw for every transformation, you can define one transformation matrix, correct?
Yes, sir.
Yes. Okay. To define a transformation matrix, we required three things. What were those three things?
So we have to there must be a function, and
Okay.
then there has to be the basis for domain and codomain. Yeah.
So those three things are the function, transformation function. Then you have a basis for the domain and the basis for the codomain. Let's suppose you had a transformation T, which is something, any transformation of your choice. Okay, so maybe I'll say the transformation was x y equal to x plus y comma x minus y. Okay, this was the transformation. Now, you defined one transformation matrix transformation matrix for the domain for the basis of domain, not for, with the basis of domain and codomain as beta 1 and gamma 1 effectively. Okay, so this transformation matrix, I'm saying this to be A. Now you defined another transformation matrix. Another transformation matrix, this time I'm calling it P. The basis of domain and codomain as beta 2 and gamma 2. So it's just like your choice of basis. If your choice of basis would differ, then it's clear that you are going to get two different matrices, correct? But there is one thing you can say about those two matrices, that A and B would be equivalent to each other.
So even if like beta 1 and beta 2 or gamma 1, gamma 2 are different bases, then also like this A and B would be equivalent to each other.
Yeah, here beta 1 and beta 2 are different,
Are
right?
different, yeah, of course. But if it is same, sorry, if it is same, then when we are going to get the same matrix.
Yeah, so it's same matrix is already equivalent, because in equivalent,
Okay,
you
yeah,
must have seen
single
that we talk about three relations. The first is it should be related to itself.
itself, yeah, yeah, sorry, yeah, yes, sir.
Yep. So if it is the same, if you talk about A and A, both are already equivalent with each other,
Fine, understood.
right? What are the other things we can talk about? Mm, equivalent matrices. Okay, so one thing is a very important point. This will help you to check whether two matrices are equivalent or not. Okay, so maybe I should make the point as how to check whether two matrices are equivalent or not. Okay, for that we have few points with us. The very first point is A and B are equivalent if and only if. It's not just if, it's if and only if. Means the only condition when it is possible. One can be obtained from the other using a sequence of linear elementary row operations. Elementary row and column operations. Okay, so A and B are equivalent if and only if one can be obtained from the other using a sequence of elementary row and column operations. Right, so
So like here like we can use both row and column operations simultaneously. Simultaneously, I mean like from A to B, from getting A to B. Uh, uh, if we do only row operations and we can possibly get B by reducing A, then and can we do both for the single time when we reduce A to B? Can we do both operations, row and column?
okay, so it's preferred that you use one operation at a time. Maybe if you're going with the row operation, you can stick to your row operations, or if you're going with the column operations, you can stick to the column operations.
Okay, sir.
Okay. Mm, one is this was one of the point. The second point is A and B are equivalent if and only if they have the same rank. Okay, so they must have the same rank. Now, how we got to this point? So there are few reasons for it. The first reason could be, mm, first of all, we are multiplying with the invertible matrix, right? So multiplying with the invertible matrix doesn't change the rank. Why? Because whenever we talk about this elementary row operations, so elementary row or maybe column operations, uh, reserves the row or maybe column rank. Column rank. So the reason is
Uh,
whenever
sir,
row space, not rank. Yeah.
so the reason you have just mentioned about the statement about that is the reason A and B are equivalent by only one can from. Yeah, that is just the reason. We can get REF of a matrix by just multiplying with an invertible matrix.
Yeah, it is correct that
And
uh,
so,
see,
yeah.
mhm,
And getting the REF will preserve not only rank and determinant also. The row space or column
uh,
space won't change. So that's the reason.
I see getting the REF doesn't preserve your determinant. Your determinant changes. Okay, if I have R as the RREF of my matrix, then I cannot say that determinant of A is going to be determinant of uh, my R. Okay, because in elementary row operations or column operations, I am allowed to scale a row or a column by any scalar value, right? But we know if you scale any row or column, what would happen? The value of your determinant would be changed. So you cannot say that if you are doing elementary row operations, then the value of your determinant would not change. Okay, so that is not something you can do. But if you want the reasons for this point, the reason is any invertible matrix is product of invertible matrices. So see this P and Q. Okay, P is a invertible matrix, right? And it's an elementary matrix with us, for us. Right? So what P is actually stores the data of the sequence of row operations that we have done, elementary row operations that we have done. Okay, whereas Q stores is storing the data of elementary column operations that we have done. So whenever we are doing any elementary row operations, it's getting stored inside my P. So it's just and every elementary row operation can be written in a form of a matrix. You are just pre-multiplying with any elementary matrix whenever you are doing a row operation. So when you just take the product of the sequence of row operations that you have done, you obtain this elementary matrix P. And since it's a non-invertible matrix, then you get the guarantee that none of the matrix that you had. Uh, okay, so if I write this thing as, give the idea. See, if I write P as the product of many invertible matrices, so I had some En, then I had some En minus 1, and then I had some E n minus 2, so on till E1. Okay, so what I can say is determinant of P actually is equal to determinant of your En, determinant of your En minus 1, and so on till determinant of your E1. Now, if the determinant of P is not equal to 0, if determinant of P is not equal to 0, this implies the determinant of En is also not equal to 0. Okay, maybe we can write it like this. En or your En minus 1 or your determinant of E1, none of them has a 0 determinant. Right, so if P is an elementary matrix, that means its determinant is non-zero, right? So this also means if P is represented in a form of elementary matrix, then if P is represented in a form of product of matrices, then all the matrices are also elementary. Why? Because their determinant is also not equal to 0. Right? So any invertible matrix can be represented as a product of many invertible matrices. This is the conclusion you get from here. Okay, so whenever you are doing P, whenever you are pre-multiplying with P, actually you are doing a lot of elementary uh, operations. Okay, row operations to be more precise. Whenever you are post multiplying with Q, you are doing a lot of column operations. Okay, so it's like if you want to obtain A from B, you just need to do some sequence of row or column operations and then you will get there. So this was the idea behind this line. Whereas TIONS operations, so if you have row space in the week 3 or 4, maybe we saw how to calculate, how to determine the row space or column space, right? So a row space is just the set of linear combinations of your rows, where column space is just the set of linear combinations of your columns. So whenever you do the row operations, elementary row operations, you preserve your row space. Your row space doesn't change. And whenever you do elementary column operations, your column space doesn't change. So that means uh, there is one more thing you should keep in your mind, that whenever you do elementary row operations, uh, reserves the rank of column space, whereas the elementary uh, column operations reserves the rank of row space. Okay, and we have seen one thing, that rank of column space and rank of row space is same. Right, so overall we can say that uh, if A and B are equivalent, you are just doing elementary row or column transformations. So whenever you do elementary row or column operations, it doesn't change your rank. So if A and B are equivalent, then the rank of A is equal to the rank of B. This is what we have done for the uh, equivalent matrices. Right. So now, if we solve some questions on it, before that, if you guys have any doubts, you can ask. Okay, so any doubts still here? Maybe we have completed this point. We have completed this point as well. Can be transformed into one another by a combination of elementary row and column operations. It's equivalent if and only if it has the same rank. And okay, similarity we have not done, but still we have done about equivalence. So let's try to solve some questions on equivalence. Is that fine? So maybe we'll start with our activity.
Sir,
Yes.
sir, can you explain how to get these matrices Q, A, P, given the transformation and the basics? So,
Given the transformation, how you can obtain these matrices A and Q or A and B.
yeah, given the transformation and basis for dominant codomain, how to get. Mm.
Okay, if that is the question, was it there in week 5? No, it was not, right? Yeah, here it is. Maybe we can take one example from here. Matrix of linear transformation. So whenever you want what? Whenever you want the matrix, you must have three things. First is the basis of domain, second is the basis of codomain, and third is the transformation function. So let's say this is the question that is given to you. You have the function, you have the basis of domain, you have the basis of codomain, and you want to find the matrix of transformation. So what matrix of transformation is? It's just you write the different coordinate vectors. Now, how to get these coordinate vectors? So to get a coordinate vector, what you do, uh, we did a similar procedure here. If I want to get a coordinate vector for the transformation of 1 comma 0 for this basis, what I would do, I would write it as x times of 1 comma 2 plus y times of 1 comma 1 is equal to the transformation of 1 comma 0. Okay, and whatever the value of x and y would be, that would be the element of my coordinate vector. So it's written over here. No, it does not represent your coordinate vector. It represents the matrix of transformation. Whereas these things, okay, represents the coordinate vectors. So v1, v2 are the vectors of the basis of domain. So v1, v2 will be from the basis of your domain. Okay. So, oh, yeah, here we go. So what we said we are going to write x times of 1 comma 2 plus y times of 1 comma 1 is equal to the transformation of 1 comma 0. Have we written it somewhere? Yes. X times of 1 comma 2 plus y times of 1 comma 1 is equal to transformation of uh, 1 comma 0. And transformation of 1 comma 0 is 1 comma 1. We have seen it here. Transformation of 1 comma 0 is actually 1 comma 1. Now you find the values of x and y. So the value of x was 0, the value of y was 1. So I wrote x here, y here. This was my first coordinate vector. Now similarly, I will write the same equation. X times of 1 comma 2 plus y times of 1 comma 1 is equal to transformation of 0 comma 1. That is 1 comma minus 1 here. Okay, that would give me two equations. From here also I'll get the values of x and y, and I'll represent those values of x and y as my coordinate vector. And once I have both the coordinate vectors with me, so as we previously mentioned that I just need to arrange those coordinate vectors inside a matrix. So I did that. 0 comma 1 became the first column of my transformation matrix, and minus 2 comma 3 became the first a second column of my transformation matrix. So that is how you determine the transformation matrix given the basis of domain and codomain. Done?
Yeah, that's okay, sir. But I'm asking the matrices for equivalence condition. How do we find the P and Q? Which basis we have to write in the form of a linear combination of which basis? We
Okay,
have
I got that. Okay, I got
so,
that. I got that. Oh, that's why I asked that whether you want me to talk about A and B or
yeah,
whether you want me to talk about P and Q. You said A and B, that's why we got here. No issues. We'll see P and Q as well. P and Q as well. Okay. So coming to the activities, let's discuss few of the questions, and here only we'll get the question where we'll have to solve for P and Q. Okay, so here is your very first question. This is the correct set of options. If a matrix 3 cross 3 matrix A is similar to the identity matrix of order 3, then A must be the identity matrix of order 3. So before that, maybe let's quickly finish the similar matrices as well, because I guess there are few questions on similar matrices. So what is the similar matrices? Two square matrices A and B of order n are similar if you can find an invertible matrix P of the same order such that A equal to P, B, P inverse. See, there is one thing. Here you had P, B, Q. So P and Q both were different matrices. Here P and P inverse. Here you do not have Q as a different matrices. Here you get one more condition that it's just Q equal to P inverse. Okay, so similar matrices are just special case of equivalent matrices. The only thing is instead of Q, you have P inverse, a more specific value of Q. Okay, so this being said about this similar matrices. So what can we say? If A and B are similar, then there are few points we need to keep in mind. They are equivalent. Okay, the second thing is they must have the same rank. They have the same rank. And third point is they have the same determinant. Why same determinant? Just take determinant on both the sides. It would be determinant of A equal to determinant of P into determinant of B into determinant of P inverse. And determinant of P inverse is nothing, just the inverse of determinant of P. That is 1 over determinant of P. So both these things will cancel out each other and you will be left with determinant of A equal to determinant of B. Okay, but you must keep in your mind that this condition is not uh, what you say uh, it's not vice versa. You cannot say that if the determinants are equal then the matrices are similar. No, it's wrong. Okay, but if A and B are similar, then you have these things with you. They are equivalent, they have the same rank, they have the same determinant. Okay, so I will just put one more thing. Vice versa is not true. Okay, and one example would be your minus 2i and 3i are equivalent with each other, equivalent matrices, but they are not similar. Okay, so this was about the similar matrices. Yes, you had some doubt.
sir, I'm saying they have same trace.
You were not properly audible. Sorry, could you repeat again, please?
Sir, I'm saying they have same trace also.
Yeah, they have same trace as well. So this is one more condition. Uh, they have the same trace. Okay, and again, the same condition is not vice versa. Okay, you can write few more conclusions. So conclusions is something you sit and you think and you can define multiple conclusions at once. So one of the conclusion is this as well, that the only uh, similar matrix to a scalar matrix is the matrix itself. So these are some things that you can keep in your mind if you want. Right. So I guess this was the summary of all the things that we have done till now in the live sessions. Maybe this is was the summary of your lecture one as well.
Excuse me, sir. Even if like it
Yeah.
is not vice versa is not true, it means like even if all these three or four criteria is like if it is fulfilled, they're equivalent, they have the same rank and they have the same determinant. Then also we cannot say like A and B are similar.
Yeah. This is not something. Any condition here is not vice versa. Right. So even if all the conditions are satisfied, you still have to check for the possibilities. Okay, you still have to check for first whether they are equivalent or not, and if they are equivalent, whether their determinant is same or not. So if you are able to check these two conditions, that A and B are equivalent with the same determinant, then you can call it similar. So you need not to worry about all the cases. Just check for two cases. They are equivalent and they have the same determinant. If both these conditions are satisfied, then you can say A and B are similar matrices.
Okay, fine, sir.
Is it fine? Yep. So coming back to the question that we had, uh, 3 cross 3 matrix A is similar to the identity matrix of order 3, then A must be identity matrix of order 3. What about this?
So this is true.
This is true. Why?
Sir, I've tried with an
Why?
example. That's why like I'm
The same point that we discussed, the only similar matrix to a scalar matrix
okay,
is
right?
the
Yeah.
matrix itself. So identity matrix is a scalar matrix in itself. Okay. So the next is, if a 3 cross 3 matrix A is similar to a diagonal matrix of order 3, then A must be a diagonal matrix of order 3. What can we say about this point? It is not asking here that it has to be the same matrix, but it is asking that it's also a diagonal matrix. So do we have something for this? Do we have something for this? Any idea? Yes, no.
No, sir.
So why no?
Like it is here we can see like 3 cross 3 matrix. It is similar to a diagonal matrix of order 3.
Okay, so let's take an example. Okay, an example would do a lot for us. So we are taking, let's say, A equal to the most simple example we can think of. So let's try with a matrix, and here we have 3 cross 3, 3 rows, 3 columns. Correct. Let's copy that. It will help us. So I had to take any diagonal matrix, right? So I am taking the simplest diagonal matrix, maybe this. Okay, so this is my A. What about B? So I'm taking the same matrix again, but this time I'm making one change. Writing 2 over here. Now, if A and B are equivalent, what about this? Yes or no? Yes or no?
Yes, sir.
The rank is same.
They are equivalent because you just do a rank operation, a row operation, right? Where you are just adding this row to this row. Okay. And you get B. Right? So you are just doing the elementary row operation. So by doing an elementary row operation on A, you can obtain B. Hence, they are equivalent. Yes.
But the only scalar matrix to scalar matrix is the matrix itself. It is telling.
But it's not a scalar matrix. But it's not a scalar matrix, right? R1.
That matrix itself mean I don't understand.
This is not a scalar matrix. It's okay. You are saying
Oh,
that
okay, okay, oh, okay, okay. Understood, understood.
it's a diagonal matrix, not
Yeah,
scalar.
yeah.
Okay. Are A and B equivalent? Yes, they are. Are this, what about, do they have the same determinant?
Determinant.
Yes, sir.
Yes, yes.
Yes. Why? Because just doing this row operation will not change the determinant of A and determinant of B, right? So A was A and B are similar matrices. I can conclude from here. Okay. Here A was diagonal matrix, but B needs not to be a diagonal matrix. Is that fine? Is that fine?
Yes, sir.
Okay.
Sir, last one, how we are telling A and B are similar? What is the concept you are applying?
So for A and B to be similar, you need to check for two cases. A and B must be equivalent and they should have the same determinant. Here we highlighted these 2 points. If you simultaneously satisfy both these points, okay, then you can say A and B are similar.
What about other conditions? The same rank and same trace.
See, if they are equivalent, uh, you can say that they will have the same rank,
Yeah,
correct?
yeah.
So it's these are not the conditions required. These are the conclusions you can make out of this statement.
Oh, if A and B are, A
Maybe
and B are similar, the converse is it true?
we our conclusion. Yeah, converse is not true. That's what we have written.
Yeah. For counter example only, we can take these results. If it is
Or for
not
counter
satisfied,
example, you have this.
yeah, not similar.
Conditions for A and B to be similar. And from for here, you can maybe put these 2 points. This is the first. This is the second. And these are the conclusions.
Necessary conditions, but not sufficient conditions.
No, if both these conditions are true, then A and B are similar. And these are the conclusions you can derive from if A and B are similar.
So if just write if for both the conditions. A and B are similar if its determinant is non-zero and what is that?
A
Determinant
and
are
B are similar if they are equivalent and have the same determinant. That is the two conditions that we need.
okay.
Okay, so we have written the heading conditions for them to be
Equivalent,
similar.
how you are checking that by applying row elementary transformation it will be equal.
For equivalent, we saw that if one matrix could be obtained by another matrix.
Oh,
Okay, so here B could be obtained by A if we just do
okay,
this
okay.
operation R1 plus
Yeah,
R2.
yeah. Okay, okay.
Okay, so what about this point? A and B are similar matrices, then they are also equivalent matrices, right? So if they are similar, they are equivalent.
True.
Okay, that is true. This is the conclusion, right? But the vice versa for a single matrix is not true. Here we have seen that 2i and 3i are equivalent, but they are not similar. So this point is true, but this point is not true. Okay, so maybe if I take this screenshot and paste it here, I will get the context of whatever we have written. Yeah. Now moving on to the next question, we have a transformation that is defined from R3 to R2. This is your transformation, and it is asking that consider two bases. This is the first basis, this is the second basis of R3, and consider the standard ordered basis of R2. Let A and B be the matrices corresponding to the linear transformation T with respect to the bases B1 and B2 for the domain respectively, and a gamma for the codomain. Let Q and P be the matrices such that B is equal to QAP. Now, which of the following matrices represents A? So your first question would be which matrix represents A, second would be which matrix represents B, and third would be which matrix represents Q and P. Correct? So what is your A? A is basis of domain is beta 1 and basis of codomain is gamma. What is gamma? Gamma is the standard ordered basis for R2. It's 1, 0, 0, 1. Okay. So this we did in week what? Week 6. That if you have got the basis and if you have got, okay, maybe let's take the screenshot. This we have done. If you have got the basis for domain and codomain, how you can find the matrix of transformation. Okay, so if we write the heading as to find A. Okay, so how will we find A? First of all, A is my transformation matrix for my codomain being gamma and the domain being uh, beta 1. Right, so how will I do that? Any idea? Is it going to be x times of 1 comma 0 plus y times of 0 comma 1 is equal to the transformation of your v1 vector of basis 1 0 0? What would be the transformation of 1 0 0? It's going to be 1. It's going to be 1 comma y plus z. Y plus z is 0.
0.
So x equal to 1, y equal to 0. Correct. Similarly, x times of 1 comma 0 plus y times of 0 comma 1 is going to be the transformation of 0 1 0. What it would be? 0 1 0. It's going to be
minus 1
minus 1 1.
1
So what would be your x?
x
X would be minus 1, y would be 1. And x of again the same thing. This time it's going to be 0 0 1. What it would give you? It would give you maybe 0 and 1. And that means x equal to 0, y equal to 1. Right, so what would be your A? Your A is going to be a matrix having 3 columns. And what are those columns? First is 1 comma 0. The next column is minus 1 comma 1. And the third column is 0 comma 1. When I find any option like this here, 1 minus 1 0,
second option
0 1 1. So second option is correct. Which of the following can be P? Right, so the question is which of the following can be P? So how to do that? How can we find the value of P? P is something we are pre-multiplying in what? To find P. So we need to do some row operations on B. P is going to be a matrix of order what? First of all, P is going to be a matrix of order what? So what's the order of A? The order of A is 2
2
cross 3. 2 cross 3, right?
yeah
So the order of P is going to be
3
2 cross 2. Is it fine? Because since a P is an invertible matrix of order m cross m, whereas m is the number of rows in A. Right, so P is going to be a 2 cross 2 matrix. So first, let's see, do we have any 2 cross 2 matrix here? Okay, okay, they have defined it in a different way. My bad. So
Sir, it's in
in
the
this
three bus.
question, yeah, in this question, it's not PAQ, it's actually QAP. QAP. So it should be 3 cross 3 since P is in order n cross n, whereas n is the number of columns in A. Okay, so we have seen that n is a number of columns in A. Now the question is, how can we find the Q? So for Q, we have to express ordered basis. What are what is this? Just give me a second, right? Beta 1, beta 2, gamma 1, gamma 2. Are from your okay, got it. For P, what we do? For P, we represent the basis of the vectors of basis of codomain. One has the linear combination of the basis of codomain 2. Correct? That is what we used to do. Am I correct? Can you, any one of you confirm? We press the vectors of gamma 1, gamma 2 maybe, as the linear combination of the vectors of gamma 1 and the matrix obtained by the coefficients of the vectors of gamma 1 gives the matrix P. Is it? Is it the way we do it? So because gamma 1 and gamma 2 are equal, right? Both gamma 1 and gamma 2 are your gamma, which is again equal to your 1 comma 0 and 0 comma 1, which is again, oh sorry, my bad.
Yes, sir.
Again,
Sir, isn't it beta 2 in terms of beta 1?
yeah, it's going to be beta 2. The confusion is happening because of this. We are writing it in the form of QAP, right? Because I usually prefer it writing in the form of PAQ. That's why the confusion is there. Now it's fine. Okay, now it would be fine. Now you have beta 1 as standard ordered basis. It's the 101.
Sir, you can just copy.
Sorry. Now what? The task is to determine the values of x, y, z so that I can express this 100 plus y times of 010 plus z times of 001. So what would be the value of x, y, z? So the value of x is going to be 1, y is going to be 0, and z is going to be
1.
0. Correct. Again, now this
Sir,
time
z
I
equal to
will
1.
do the same for,
Sir, z equal to 1.
yeah, z equal to 1. Now I'm going to repeat the same process for equal to 0, 1, 0. Not 0, 1, 0, sorry, 0, 1, 1. Okay, so again,
X equal to 0, Y equal to 1,
equal to
Z equal to
1
1.
and Z equal to 1. And if we repeat the same process for 1, 1, 0, we are going to get X equal
X
to
equal
1,
to 1, Y
Y
equal to 1.
equal to 1, and Z equal to 0. So from here, the matrix P is going to be P cross 3 matrix, where we have first this row 1, 0, 1, 1, 0, 1. Then we have got this 0, 1, 1, and then we have this 1, 1, 0. So this is our P. So this confusion arrived because of this format. So if you are writing P in the last, this is your P, then you express beta 2 as the linear combinations of the vectors of beta 1. Okay, the matrix obtained by the coefficients of the vectors of beta 1. So here the coefficients were 1, 0, 1. So that become my first column. 0, 1, 1 became my second column, and 1, 1, 0 became my third column. Okay, so that would be my P. So my P is it going to be this?
Sir, which software it is without all are typing?
This is MathCha.
Oh, Math. Is it free downloadable or payable?
No, no, you can download it. You need not to download it as well. You can just use it on Chrome on
Oh,
your browser.
okay. Thank you.
Which of the
Sir,
following statements? Yeah,
sir, even for the similar one also, it's P inverse P as uh, P inverse AP as mentioned in the lecture.
P inverse
AP,
AP.
B is equal to P inverse AP for similar one.
That,
This is for
that is fine. That is fine. You can. It's just a format of writing it. Whether you write P first or Q first, that would not matter. But the thing is, the things you will derive from it would change a lot, right? So it's just know it like this. If you want to find the post multiplication matrix, then it depends on the vectors of sorry bases of domains. And if you want to find the pre-multiplied matrix, then it depends on the basis of codomain. Okay, so if I say to find Q, can I write the similar conclusions about Q? The order of, if from here I'll write, but this time instead of P, I will write Q. The order of Q is going to be 2 cross 2, since Q is an invertible matrix of order m cross m, where m is the number of rows in A. Is it so? Now if you want to find the P, not P, Q. So if you want to find the Q, then what you do? In any case, instead of beta, we are going to use gamma. And here also, it's going to be gamma. Okay. So since we have got this gamma 1 equal to gamma 2 equal to your gamma 1, right? So Q is an identity matrix of order 2 cross 2. Is it fine? How I identity matrix? So see, if you represent, let's say what it's going to be, it's going to be 1 comma 0 equal to x times of 1 comma 0 plus y times of 0 comma 1. So first your x will be 1 and y would be 0. And in the second case, you will be doing x times 0 comma 1 is equal to x times of 1 comma 0 plus y times of 0 comma 1. So in that case, your x will be 0 and y would be 1. So overall, you are going to get a identity matrix of order 2 cross 2. You can repeat the same process for the vectors of gamma 1 and gamma 2, right? You can for check to check that you can just repeat the process for these two things and you will get that Q is a identity matrix of order 2 cross 2. So here whatever the matrix Q P we choose, Q is always unique and Q can be the identity matrix of order 2. Okay. Is there any doubt in this point that we just discussed? Anyone? Is there any doubt in this point? We have done P, Q, A, everything.
Said like this is not. Can you go back to please the slides? Yes. So like here gamma 1 equal to gamma 2, since they are equal, like it is gamma only, so we can like, and also it is ordered basis, also standard order basis, not only order. So we can say like this is an identity matrix, or is it like a general thing if this
Not
happens?
Yeah, not a general thing. It's just the
Okay.
calculations that you have done. So it's like you did x times of 1 comma 0 plus y times of 0 comma 1 and you equated it with 1 comma 0. So what you got? You got x equal to 1, y equal to 0. Now you repeated the same process for 0 comma 1. Okay, so you got x equal to 0, y equal to 1. Then what's your Q? Your Q is a matrix where you have 1 0 0 1. So this is what we followed. Means this is something we could solve from here only.
Okay, sir.
Okay, so moving on to the next question. If two square matrices of the same order have the same determinant, then they must be similar to each other. You have two square matrices, they have the same order, they have the same determinant, and it is saying that then they must be similar to each other. So is it
No,
correct or not?
No, sir.
no,
Right? So it's not correct. Why? Any counter example? Any counter example?
sir. A matrix and its REF form.
Sorry.
A matrix and its no, REF form. If we do some row operations, then the determinant will change. But still,
REF
they
of
will be
the
sure.
matrix can have, see, a matrix and its REF are actually equivalent with each other and their determinants are not same. Is there any other example? Because that would not be a correct example. Any counter example? Maybe if I talk about any matrix, any two matrices that have zero determinant. Maybe if I take this example, let's leave it for now. I'll just write counter example in 1 second, okay? Similar matrix and has a unique solution. And then Bx equal to A also have a unique solution, yes. Okay, counter a example for option 1. What it could be?
2 by 2
Two
matrix.
square matrices have same order. So let's take any 2 by 2 matrix of order 2. So if I have A equal to
0 1.
yeah. So if I take it 1 0 0 0, okay, and B equal to again 0 0 0 0, okay, A and B have same determinant, but they are not equivalent and similar as well. Why? Rank of A is not equal to your rank of B. Is it fine?
Yes.
Now, what about option 2? It is correct, yes. Similar matrices have same rank. What about option C? If A and B are similar matrices, then Ax equal to B has a solution, and Bx equal to B also has a unique solution. Why? If we talk about option 3, what could be the reason?
Having same rank.
C. Okay. Okay, maybe let's do this. Sorry. If Ax equal to B has a unique solution, then we know that determinant of sorry, and we know that determinant of A is not equal to 0, correct? And since A and B are similar, determinant of B is equal to determinant of A is not equal to 0. Hence, determinant of B is also not equal to 0. Hence, Bx equal to B also has a unique solution, and again the reason is determinant of B not equal to 0. Okay, so option 3 is correct as well. Any doubt in this one?
No, sir.
Okay, 6. Determinant of A or determinant of B is non-zero when AB and BA are similar. Okay, is it based on some? Okay, it's random. If determinant of A or determinant of B is non-zero, then AB and BA are similar. Okay, do you have anything for it? Is it true or not, or false?
False.
False, right? Because there is no such
We are not
condition
seen
that
like
if
this.
the
Yes, we are not seen any property like this.
yeah. What about this? Are they similar?
Yes, sir.
Okay, so how would you say that they are similar with each other?
Having same.
Determinant is M and B.
Uh, Determinant is
No,
same.
sir.
Are they equivalent?
Sir, they are not similar because the trace is not there.
See, trace here is uh, trace here is 5 and trace here is 4. So if the trace is not same, then we can say that they are not similar, right? Because if they would have been similar, you will get the same trace for both the matrices. But since the trace is not same, we can conclude they are not similar. What about this one? Option C.
Determinant is not same.
Determinant is not same. And what about this one?
Similar. It is similar. It is actually not similar.
I think it's not similar.
So see, determinant is 4. Determinant is 4 and they are equivalent with each other as well. Correct? So this is similar. So the question was set of correct options. So this is incorrect. This is incorrect. This is incorrect. If this has to be correct, then what is going on?
So I think they are not similar, sir. The last option.
They are equivalent with each other or their determinant is same, whether they are equivalent with each other or not. So A
Sir, scalar matrix is it is. So it must be similar to itself only. So that it is not similar.
Oh yes. So this option is correct. It's a scalar matrix. Then it has to be similar with itself.
So the second option I did not get.
Just 1 second. I had doubt in one thing. It could be obtained by B. Can you obtain B by using A minus half of? If you do R1 minus half of R2, shouldn't you get B again? Yeah, since it's a scalar matrix, it has to be scalar only. Okay, we'll look more into it. What about this option? If determinant of A or determinant of B is non-zero, then AB and BA are similar.
Sir, shall we check some 2 by 2 matrix?
Okay, for it to be similar, see, first of all, what are the things we can write? If A and B have, if A, B have determinant, they are square matrices of same order, right? So we need to prove
Sir,
yeah.
both determinants have to be non-zero. Both determinants of A and B should be non-zero.
A and B could be written as something like this. Sorry, AB and BA. Determinant of A or determinant of B is non-zero. One of them has non-zero determinant. One of them has non-zero determinant. Given determinant of A or determinant of B is non-zero. The one thing we can prove that one thing so we have that determinant of AB is equal to determinant of BA. That is fine. What about the second case? How we can come till here? Okay. Got it. Let's suppose a, a determinant of A is non-zero. Hence, A is invertible. So what can I do if A is invertible? So I will say that if I have AB, I will write AB in the form of A. This is what we have to prove, right? A inverse B. So AB is just, yeah, got it.
Identity into identity.
No, not identity. This is what we will write.
Sir, we can take cases.
Just give me a second, please. Okay, B is this. This is BA. B is equal to AB into A inverse. What about this? So from here you can write AB equal to some matrix A into BA into the inverse of the same matrix. So now we have represented AB in the form of some matrix P into BA into uh, P inverse. So hence AB are AB and BA are what similar if A and B are square matrices and one of them, if one of the A the matrix in B has a non-zero. Okay, this is the proof for your option 1.
Sir, both have to be non-zero. Both A and B have to be invertible. Then only the product of matrices will be invertible.
Yes, sir.
Both have to be
If
invert.
the product of
No, both.
matrices are AB or no, sir.
So we are not saying invertible. We are not talking that whether AB inverse or BA inverse exists or not. We just wanted to express AB and BA in such a manner. So even if I talk about this, uh, if I say I into 0 and 0 into I are similar.
Sir, how
Correct?
you are writing last step AB? Last step AB equal to P
Yes.
dot and the A equal to P. How you are writing?
Yeah. It's just like to prove that I just had to express AB in this form. And
That
what
is
I
okay.
did
First
was
two steps
I
over.
just
Third step only. Yeah.
just A is some matrix P. Only that is enough. But if you just want to see it in some other form, or if you are getting confused by looking at it, so you can write it in a form of P as
A
well.
equal to P. Is it A equal to P?
A equal to P, yes. Okay, so both need not to be what? 0. See, determinant of I is non-zero, determinant of 0 is 0. But I into 0 and 0 into I are similar matrices. So even if one of the square matrix has a non-zero
Sir,
determinant,
but the determinant are not same. No, zero matrix is determinant is zero. Identity matrix is n. How it is similar?
similar, see, I and 0 are not similar. I into 0 and 0 into I are similar. Here we are not saying A and B are similar. We are saying
Oh,
AB and BA are similar. Okay, and so these two options were there.
sir, are you opening any notebook in the Matchaya editor?
Uh, Yeah, just a file.
But notebooks, how to open? I sign in, but it is not. Yeah.
Just
Okay.
create a new file
Okay.
and just start writing.
Okay. I try.
6 we have done. In 7 what we have, two invertible matrices of same order are equivalent. What about this option? Two invertible matrices having the same order. Why this option is correct? Any idea?
Sir, if they are invertible, they will have a full rank.
Sorry?
If two matrices are invertible, then they will have a full rank. No? And the same, they have same order, so they will have the same rank.
So from rank you cannot determine that, but one thing you can do. If uh, both the matrices of same order are invertible. This would say that their RREF is a is an identity matrix. Okay, both have same RREF. Both having same RREF means one can obtain another by doing some elementary row operations. Is it fine? Is it fine?
Yes, sir. Sir, what are correct options for the previous question?
Sorry, could you repeat, please?
Uh, for the previous question, what are correct options?
Previous question, the correct options were this. Why this option is correct? Because for a scalar matrix, only similar
The
matrix
matrix
is the
is
matrix itself.
okay. Okay, sir.
Next question is regarding this. So you can check whether they are equivalent or not. Here also you can check whether they are equivalent or not. Okay, so maybe here 12, 12. This has zero determinant. This does not have any zero determinant. So their ranks are different. Its rank is 1, its rank is 2. So these are not equivalent. What about this one? So again, you can check for this example as well. Consider two linear transformations. Let A and B denote the matrix representation of T1 and T2 with respect to the standard basis of R3. Then A and B are equivalent. What about this option? You have got two transformations, okay, and you want to comment on the transformation matrix of both the transformations. How can we do that? So do we have
Uh,
to Mhm.
Sir, we write the matrices here using the coefficients. Coefficients of the equations will be the elements in the rows respectively. A will have 1, 1, minus 1, 1, 4, minus 2, and minus 2, 1, 1 as well. And respectively for B as well. Then we can check their equivalent of.
Could you repeat the thing again, please?
Sir, in this case, these are a standard basis, right?
Mhm.
For both domain and codomain. So in this case, we can apply a trick. Like we can take the coefficients directly. The coefficients of each element from the transformation. So, uh, x plus y minus z is uh, from those we can take the coefficients as the rows. For A,
How
we can
many
take
rows will you get?
we get three rows for matrix A and for matrix
Uh,
B.
how
One
many
one
rows? So
minus
is it
one.
going to be a 3 cross 3 matrix?
Yeah, we get three cross three matrix for A and B as well. For
So 1,
B,
1
we get
minus 1.
um, For B, we get actually a 3 by 2 matrix. And for A, we get a 3 by 3 matrix.
Okay, so here actually we are dealing with the standard basis of R3. So what's standard basis of R3? It's 1 0 0, 0 1 0, and 0 0 1. So based on that standard matrix, first let's try to see the T1, how T1 would react. Okay, so if we get any conclusion for the standard matrix, we'll use the same conclusion on T2 as well. So what's the first step? The first step is just to write xyz equal to x times of 100, a times of 100 plus b times of 010 plus c times of 001. So from there you get the conclusion that xyz is actually equal to a comma b comma c. That means x equal to a, y equal to b, and z equal to c. Fine, that is the first conclusion that we get. Now the second thing is to determine the what? To determine the coordinate vectors. So what's going to be my first coordinate vector? For the first coordinate vector, I will check this x plus y minus z. So if I put 1 0 0 here, what I'm going to get? I'm going to get
1 1 minus 2.
not no not 1 1 minus 2. It's going to be minus 1 in this case, right? It's going to be, yeah, it's going to be 1 in this case. In this case, it's going to be 4. And in this case, it's going to be 1. Correct? Transformation of 1 0 0 is going to be what? Is going to be 1 4 1. Is it correct? 1 4 1. The
So I
value
think
of
it is 1 1
ABC.
and it cannot be 4, sir, because if you're taking a value as
Oh,
x
sorry.
as
Sorry,
1 here.
sorry. It's 1 1 minus 2. Now is it fine? 1 1 minus 2.
Yes.
Yes. So the first coordinate vector is going to be 1 1 minus 2. The second coordinate vector is going to be 1 4 and 1. And the third coordinate vector is going to be minus 1 minus 2 and 1. Okay. So whenever we talk about the standard basis and we want to check for the A is what? A is just about T1 matrix for T1. So okay, matrix of order 3 cross 3. So what would be it? It would be 1 1 minus 2 will be my first coordinate vector. 1 1 minus 2 is the first coordinate vector. What about the second coordinate vector? It's going to be the coefficients of y. 1 4 1 1 4 1. What about column 3? It's my third coordinate vector, that is the coefficients of z. Minus 1 minus 2 1. Minus 1 minus 2 1. Now, if I talk about B, for B, I will be doing the same for T2. So this time I can directly write this maybe. E control E. Here I get 1 1 0. And then it's going to be 1 0 minus 1. And then it's going to be 0 1 1. So again, you have two matrices, and now check whether A and B are equivalent or not. So this was a task that we have done. Okay. So any doubt in this one? Any doubt still here?
No, sir.
Sir, are you
Okay.
using sniping tool to cut and paste?
Sorry.
Are you using sniping tool for to cut and paste?
Yeah, I'm taking snippets, screenshots, and pasting it there.
That is sniping tool.
Yeah, sniping tool. Yeah.
Okay.
Let E be the set of 2 cross 2 matrices which are similar to the scalar matrix this. So E be the set of 2 cross 2 matrices which are similar to a scalar matrix is this. So E will have only one element that is going to be the matrix itself. So E is a singleton set. Okay, and it is finite cardinality. Cardinality means number of elements. So if it has only one element, so its cardinality is 1, which is a finite number. Okay, any doubts here?
The two elements are there. How we are telling singleton set?
Why there are two elements? It's just a single element. Matrix similar to this is just 3003.
So generator only you have to take.
Sorry?
Generator or basis only you have to take collection, but because the E contains E, what is E?
E is a set of matrix which are similar to this. So the only matrix which is similar to the matrix is the matrix itself. So E will have only one element, that is this matrix, 3003 matrix.
But 0 is not counted as element.
No,
Is it?
not 0. See, what would be E? If I write here just for a minute later, E is just this. This is the set. So, cardinality of E means number of elements in E. E has a single element. Okay. And what was the question? The question was E is the set of matrices similar to
Okay, I
this.
understood.
Hello. Okay, so this is again what we have done. One or two more questions are left, I guess. Which of the following options is are true? A and B are similar matrices. Then A inverse and B inverse are similar matrices. What about this? A and B are similar matrices. So if they are similar, their inverses would also be similar. Can you say that?
Yeah. Yes.
Okay, is there any reason for that?
Sir,
Both are
determining
invertible.
of
In inverse also invertible. A inverse whole inverse equal to A.
If
A,
they have the same determinant,
yeah.
then determinant of A inverse and determinant of B inverse is also going to be same. But how can you say that those are similar? You'll have to write some proof. Whenever we talk about linear algebra, there have to be some proof. So A and B are similar implies proof. A inverse and B inverse are similar. Now, how would you do that? What is the given information? The given information is A could be written as something P into A into P inverse. P into A, B into P inverse. What is A inverse? A inverse in that case is going to
P
be
into P
inverse of inverse of
whole inverse.
this thing, and what that would be? That would be
Uh,
P
P,
inverse
P
whole
inverse, P
inverse,
inverse.
PB,
inverse,
PB whole inverse.
then B inverse, and then it's
P
going to
inverse.
be
P inverse.
P inverse,
It's coming.
and that would give you P into B into P inverse. So again, we expressed A inverse in a form of something B inverse. So A inverse, B inverse are proved, hence proved. So we used one property here. What was that property? We'll put it here maybe. The background noise is coming, Prakash, from your side.
Oh,
Could you
sorry,
mute
sorry.
your uh, property is if you have some matrix XYZ, I should write XYZ, and you're talking about XYZ whole inverse. It's something that we did in week one. So week 1 or 2 maybe. So it's going to be ZYX. So it's Z inverse, Y inverse, and X inverse. So this is the property that we have used here. Similarly, just don't directly jump to the conclusions. Think for everything. A and B and A square, B square. What about this? A square, B square. How can we do that?
Try.
So we can square on both sides, and I think we'll,
Yeah, so this
for the
time we will
given.
have to prove instead of A square, this would be this. Now what? If it's a square, so it will not be this, but it would be XYZ square, square, square. So it would be some P square times B square times P power minus 2, right? And again, this could be written as A square is equal to some matrix P square into B into P of minus 2 can be written as P of 2 inverse. So again, it's proof. Okay. Any doubts? What about this? Can you make any conclusion for A and B out of it? Should be B. Okay. Is there any doubt in this proof? Hello.
No, sir, it's fine.
Now it's like A square and B square are similar. From there, can you write the vice versa? That A square and B square are similar. Will A B and B are similar? Hmm? See, one thing for sure, you cannot say A power 1/2. Okay, in matrices we do not have that. So I don't think
So
there is
like,
any way going from C. Yeah, please continue.
excuse me, sir. So like here,
Yeah.
for this proof only, where we have proved that A and B are similar, then we prove that A square and B square are also similar. So this cannot work vice versa, sir, I think.
Yes, it cannot work vice versa. Why it cannot work vice versa? Because
Shall
you
we give
cannot say power
the
1/2.
counter examples?
You will no, not about complex number. You cannot have
Counter
some
example.
fraction power here. Counter example for what?
A square, B square are similar, but A and B are not similar.
Uh, You'll have to think about it. We'll have to think about it. Okay, because we'll have to take two matrices which are square of some matrices. Then if we'll have to think about it. It's not some easy example. It's going to be something complex. But one thing I'll say that how you can show that it's not going anywhere. Converse is not true, or mm,
Sir, can't we go reverse like this? P square, B square from last step to first step? Where it
see,
is?
yeah, that's what I was telling. Here, you will have to take from if you go in the reverse order till here, you will have no issues.
Yeah.
But you cannot take root on both the sides because it's equivalent to multiplying with the power half. Okay, and fraction power of matrices you must have not seen. Okay, so from here you cannot jump here. That is the only problem.
Oh.
From here to here, all the steps are reversible. But this step is not reversible. Okay, so maybe I just write
Sir,
here. Yes.
sir, you can take example A is equal to 1, 0, 0, minus 1 and B is equal to minus 1, 0, 0, 1.
What is it?
A is equal to minus 1, 0, 0, 1,
Minus 1, 0.
minus 1, 0, 0, minus 1. and B is equal to
Yeah, that
0,
is a
1.
good example.
Sir, 0, 1, sir. The second row,
B
0, 1.
0 1 and just
Uh,
give me a second, please. We got one example actually. 0 1. Here, see, A and B are not.
okay.
Array, this step is not reversible. Are not similar, but A square is equal to B square is equal to 1 0 0 1. Here A square and B square are inversible, are similar, sorry. So we saw that if A square is equal to E square and B square are similar, that does not imply A and B are similar. Okay. Is it fine?
Yes, sir. Like, sir, like by proving with only the alphabet, like using the not like non like example, without example, like we have tried proving for the previous thing where A and B are similar, and then we prove that A square and B square are also similar. So like that, I have tried for A cube and B cube also. For like for A cube and B cube and or A to the power 4 or B to the power 4, I've tried like, and all of them are similar.
Mhm.
But there is like no way of coming back. But
Yeah, you
again,
cannot
this
come back.
only this example can give satisfaction that yes, it it is not like that A square and B square are similar, then A and B are also similar.
Yep. And A and B are similar, then A transpose and B transpose are similar. So how would you prove that? So it's going to be actually very similar to this. Where is it? So transpose and inverse, they have their very common properties. So instead of just use T, even this property is also same. So for square, we had to change this property, but for transpose, this property works fine. Transpose, transpose. And now instead of this, just we are going to write that P inverse transpose actually is equal to P transpose inverse. This is also one of the property, right? That you can write this thing as this thing. Okay. Is it fine? Is it fine? Hello, hello.
Yes.
Fine. Hence the last question. Let us consider the following matrices. A and B have the same rank. Sorry, these are the questions and same determinant, but they are not similar matrices. A and B. What can you say about A and B? Their rank is same, their determinant is same, but still they are not similar matrices. Why? Because B is a scalar matrix, and a scalar matrix is similar to itself only. Correct?
Yes, sir.
Okay. A and C have the same rank and the same determinant, but they are not similar matrices. So what about A and C? So rank is 2, their determinant is 1 and 1. Are they similar with each other? Actually, yes. They are similar with each other. Right, no?
Yes, sir.
They are similar with each other because
Same.
it's just you have just exchanged the rows. You have not done anything else. So yeah, they are similar. So this
But
option is not correct.
so like A and C have not the same rank. Like here it is written the
Same,
same
they
rank.
have the same rank, right? Rank of A is 2.
Rank of A is
Rank of
2.
C is 2. Rank of B is also 2. All ABC have the same rank.
Okay. Okay, rank. Yeah. Sorry.
All have the same determinant as well. A and B are not similar. B and C are not similar, but A and C are similar. Okay, so this is the conclusion. A and B are not similar. B and C are not similar, but A and C are similar.
Sir, we have to check eigenvalues also, I think. Eigenvalues are same
Uh,
means I think both are similar.
Actually, you don't have eigenvalues here in Match 2. You'll get that in
So like in
MLL.
the second option, sir, so A and C have the same rank. That is
Mhm.
understood, but and the same determinant also. Okay, fine. But they are not similar matrices.
They are
And you
actually
are
similar.
like saying it is similar. Okay.
So
They are
not similar
similar
is incorrect option.
because
It just
we can
exchange these
only
two rows.
okay, okay,
1
okay,
0
fine.
0.
Yes. Yeah. Thank you, sir.
Sir, can we check that A and C have same eigenvalues? Shall we check?
Okay, so because it's not here in our syllabus, so we'll actually leave it for now. Okay, you just post it in discourse. There we'll answer. Okay,
Oh,
will that work?
Uh,
Okay, so
Sir,
that was.
maybe
Mhm.
we can take an arbitrary matrix P of size 2. Then we can check AP is equal to PC.
You can take what? Could you repeat, please?
Sir, I am saying we can take an arbitrary matrix P of size
Mm-hmm.
2, and we can maybe check AP is equal to PC. Then if we are able to find uh, matrix P, then we can conclude with certainty.
Could you repeat once again, please? Sorry, I'm not able to get that.
Sir, to check whether A and C are similar, um,
Mhm.
we have the most accurate condition is A is equal to P inverse C P, right? So we can just pre-multiply P on both sides. So we get PA is equal to CP. Right. That condition we can check by taking an arbitrary matrix P.
See, for that actually, no, you can, uh, what do we say? That's fine that you can evaluate P and Q. Yeah, that is also one of the things that you can do. And still, if we can just see and just see that they are not similar, then why do we need to do so many things? And if we can just see they are similar, then why do we need to do some things? Why do we need to do all the steps? But yeah, whenever you are stuck, you can always go back to your basics and check. Okay,
But sir, how
but
do we
again,
make sure A and C
mhm,
are similar?
how can we?
How can we make sure A and C are similar?
Okay, for that you can check for their equivalence, and again you have check for their equivalence, check for their determinant, and if you don't get any hint, just try to find the matrix P and Q. But see, because you do not have your basis with you, how will you find P and Q? That is again one of the question, right? So, what your P and Q represents? Your P and Q represents some elementary matrices that you have pre-multiplied and post-multiplied. Means they corresponds to a series of elementary row or column operations. So your task is to check that is it possible to do some kind of row operations just to get what? Just to get your C. So can you do some row operations and column operations on A so that you can get C? So if it is possible, then it's similar. So can we check that what are the operations that we can do? Okay, the first operation is just exchange the rows, and the second operation is just exchange the columns. So once you have exchanged the rows and columns, you get this.
But we can do only row operation or column operations.
No, see, whenever we talk about pre-multiplication, no, so pre-multiplication matrix enable us to do the row operations, and uh, that post-multiplication matrix allows us to do the column operations. Now, we will have to check whether those two column operations and row operations that we have done, whether they are inverses of each other or not. See, if we just take this example, okay, we'll do the caution again. What is our A? A is 1011 1011. What is C? C is, I guess it's 1101. Okay, now next task is to check how you can go from A to C. So to go from A to C, you need to exchange the rows. Row 1, and you just exchange this thing with row 2. Row 2, and then you exchange column 1 with column 2. Is it enough? 1 1
Yes.
1 0.
But sir, we cannot apply both row and column operations simultaneously.
See. We are coming there. We are coming there. Okay. So to prove A is similar to C, we need to express it in the form of A equal to sum P into C into P inverse. Okay. Any doubt still here? Okay. Now what we are saying is this pre-multiplication P, this corresponds to some row operations, elementary row operations. So again, this into C into this. So this will give you the row operation. So just tell me by which matrix I should pre-multiply if I want to exchange the rows. If I want to exchange the rows, by which matrix I should pre-multiply the C with? What would be the matrix? That we did in the week 1.
Transpose
We have 1 0 1 1. That should become 1 1 1 0. So 1 1 1 0. Just give me a second. We'll have to do some trials and errors. 1 0 into 1 0 is 1. 1 0 is 1 0. 1 0 is going to give us 1 0 1. 1 0 is again going to give us 1. This is 8. Okay, 1 1 0 0. 1 1 0 1. That would give us 1 1 1 1 1 1 0. By which matrix we should pre-multiply if we want to exchange the rows? E. Week 1, week 1, week 1. How do we see that? We see that as linear combination of rows. So linear combination of rows, you are just exchanging, right? Instead of 1 0 0 1, you write what about this 1 0 0? Okay, sorry. 0 into 1 is 0. 2 1 is 1. Yes. What this would give you any idea? This would give you this matrix. 1 0 is 0 and then 1 1 is 1. Then you do 1 1 0 0. You do 1 0 1 1 and you do 1 1 0 0. 1 1 0 0. By which matrix it? Okay, just let's Google it. You want to swap the rows whichever row operation you do. So if for every row operation, actually the thing is you pre-multiply with any matrix. Okay, what that pre-multiplication matrix is,
0110.
that is 0 1.
10. The matrix you have A is equal to 0110 times. Okay, for first
Then
multiplication,
why it's not giving us?
I think the order needs to change. The second matrix needs to go to the front.
Oh yes. Sorry. Sorry. It's pre-multiplication. So it's 0 1 0 1 1 0 and 0 0. Yes. Sorry. I was not able to visualize this because I was, don't know why. Okay, so this is going to give you the row exchange matrix corresponding to the row swap. Then what would be the matrix corresponding to column swap? So you will take something, maybe you will take this, and you will post multiply it with some matrix of order 2 cross 2. Okay, just to get this thing. What is this thing? See. Now exchanging column, by which matrix we should post multiply?
sir, the same matrix 0110. Just post multiply this time.
Row wise 0, 1, and
110.
Yep.
So 1 times 0 is going to give us 0 and 1 times 1 is 1. 1 1 1 again, 1 0 0 again, and 1 0 is 1. Okay, that is fine. So this is the matrix with which we cross multiplied. Sorry, post multiplied, right? So now we just have to check whether the determinant of okay, maybe we pasted the wrong one. So we have to check whether these two matrices are inverse of each other or not. How will we check whether these two matrices are inverse of each other or not?
Multiply to see if it is identity.
To check P and Q are inverse of each other. So it's just going to be this into this again. And what it would give us? It will give us 1 0
Identity matrix.
0 1. Yes, so P and Q are inverse of each other. Hence, we have represented A and CS A equal to sum P into C into P inverse. Okay. So A and C are inverse of each other. Okay, so this was the mate. So whenever you do, see, I'll again say what we did here. So whenever you want to do any row operation, so every row operation corresponds to any pre-multiplication by any elementary matrix. Okay, and every column operation corresponds to post multiplication by any elementary matrix. Okay, so whatever you do, so the matrix you obtained by the row operations and the matrix you obtained by the column operations, if both the matrices are inverse of each other, then you say that your two given matrices A and C are similar to each other. So it's not just like you can say that okay, it's you can obtain A by C, hence I am saying that A and C are similar. No, there are few more things. First thing is A and C must be equivalent, the determinant is same, but still if those things are not enough to call it uh, a similar matrix, then
No,
this is the step you can refer to. These are the steps you can refer to. Okay, and how
determinant
to check? Yeah,
determinant
you
trees or rank cannot determine that the matrix is similar or not.
yes, that is the point I just write the point here. But again, I just got a bit confused on writing these matrices, though it does not take a lot of time. It's just like it's been a quite long since we have done that. But you can just check the sessions of week 1. There we did that. Okay, how to check the check the matrix that corresponds to row operations, or how to get the matrix that corresponds to the column operations. That is the thing. One caution, someone said that is not enough, right? So that brings us to a caution that if two matrices are similar, then they have same rank, determinant,
Entries.
and trace. Okay,
Yes.
but the converse is not true. Okay. So let's say, for example, if we take A as this matrix, what is it? It is 1 0 0 1, and
110.
B as this matrix, that 1 1 0 1. In that case, we'll see that A and B have same determinant,
Rank
rank,
and
and
trace.
trace,
But there
but
are
still they are not similar. Okay, so what are these conditions? So these conditions can only be used to disprove the similarity. Okay, so mm, these conditions can only be used to disprove the similarity but not to prove it. A very crucial point. Okay, so I hope this is fine.
Yes.
So we have
Yes, sir.
covered things related to your equivalent matrices and similar matrices, and I guess these things must be enough. So okay, thank you so much for that. Have a good night. Bye. Slaki.
Nice, sir. Thank you, sir.
Thank you, sir. Good night.
Thank you, sir.